Hello everyone. Today my topic is large Eddy simulation of durable bluff body stabilized flame. My topic will split into 4 sections. In this part, I will briefly introduce you some background. You know, the demand of the population technology are continuously increasing. This makes the numerical simulation of turbulence combustion become important. We know that aircraft engine is one of the most typical application in the propulsion technology, and afterburner is a key part of that aircraft engine. In the past decade, the study regarding afterburner was mainly focused on high-fidelity numerical simulation. In the 1950s, annual flame stabilizer was used in afterburner. Later, as the demand of the material aircraft increased, to ensure successful ignition even with low oxygen content, radial stabilizer has been widely used. So in this study, we will focus on the radial stabilizer. In recent years, many research have simplified the radial stabilizer to single bluff body, yield numerous results. For example, Exxon found that the BVK vortex is absent when the temperature ratio of the burner to the unburned gas is too large. Carmen studied the VGAT flame holder. As you can see, liquid fuel jet is injected into closed flow air, forming droplets, creating a thin film, and eventually break up downstream. But the existing research have some limitation. Firstly, using a single bluff body configuration does not adequately capture the complex flame interaction occurring in the annual combustor. And most of the study focus on the premixed flame. Actually, two-phase kerosene flame are widely used in realistic aircraft engine. This is still insufficient. Based on above motivation, we collaborate with Beihang University to design a novel dual bluff body flame stabilizer model for the combustion chamber. The image on the right show our experimental setup. We have a preheating device at the beginning to warm up the income flow. Next is the profountable plant, which even out the flow and give us boundary condition for our calculation. PIV mirrors the flow downstream of the bluff body. After that, we have the water cooling and the exhaust section. In this section, I will introduce you our methods and validation. As you can see, these are the governing equations of mass, moment, energy, and species. Considering the complexity of the actual task pieces, we simplify the simulation's computation domain to rectangle combustor chamber. The dimension of the bluff body are also mixed in the figure. Consisting with the experimental model, we will conduct analysis on both massing premixed flame and the kerosene no premixed flame. The calculation is performed on an open source platform named DFlame, which is based on 3 other software: Kantara, OpenFOAM, and PyTorch. We used the well subgrid model to model the subgrid stress, and the parser model to modeling the TCI turbulence combustion interaction. And we use the DF low mark form for massing for CH4 calculation and depth waveform for crossing calculation. Based on the LES method, we can capture the video. 这有个视频，你帮我播放一下。Okay. Based on the LES method, we can capture the highly complex flow field structure around the dual bluff bodies. Due to the roundly edge of the rail of the bluff bodies, flow separation phenomena are particularly complex. Inside the recirculation zone, small vortex forming initially, some of which currently develop into large vortex and eventually detach. The numerical simulation shows high consistent with the experimental result. Actually, locating peak position thus validate the credibility of the numerical method. In this section, I will introduce our result about the two flame. Firstly, in the CH4 premixed flame case, the fuel and the air are premixed at the inlet when with an equivalence ratio of 0.8. We use a chemical reaction mechanism involve 19 species and 18 for reactions. The boundary conditions we used are listed here. Firstly, we comparing the result of reactive and non-reactive flows. Significant difference can be observed. In the non-reactive flow, the BVK instability leads to periodic vortex shielding on both sides of the bluff body, forming a common vortex shield. However, in the reacting flow, the effect of the heat release and volumetric expansion suppress the BVK instability. This transforms the asymmetric vortex shielding into the symmetric vortex shielding, and the lateral movement of the vortex conform to a small range. The temperature animation shows the video can't play. Okay. The temperature animation shows that the local extinction occurs periodic in the recirculation zone at the vortex shielding. During the blow off occurring, there are significant flame stretching. And OH radical nearly cases within the recirculation zone. Two symmetrical vortex formed at the bluff body's tailing edge, drawing an unreacted and color outer mixture gas toward the central line, resulting in notable reduction in gas temperature within the recirculation zone. The accumulation of CH2O within this region prevents complex reaction, lower the heat release rate, ultimately lead to blow off. In this section, we will analyze the Kershaw flame. This flame is widely used in realistic aircraft engine. Kershaw is a spray from the injector rod located at the bluff body's front against the incoming flow direction, and it automates and evaporates due to the high temperature income flow. We use the Rosen-Raman droplet size distribution, and the break-off model and the heat transfer model is listed here. we used 7 species, 2 reaction chemical mechanism, and the boundary condition is listed here. In our investigation of Curzon flame, vortex shielding is distinctly different from that in methane flame. Despite the Curzon flame adiabatic flame temperature is higher, Kalman vortex shield still occur, differ significantly from the previous research finding. To explain this phenomenon, we propose 2 possible explanations. Firstly, incoming evaporation of droplet, incomplete evaporation of droplet makes a small amount of droplet penetrate downstream of the bluff body, so that heat release rate in the recirculation zone is reduced. As you can see, the average flow field shows the temperature field fully development downstream at the great distance from the bluff body, indicate incomplete combustion down upstream and incomplete suppression of BVK instability. Secondly, according to the flame index counter, combustion outside the shell layer is not premixed, with the inadequate mixing of fuel and air, result in incomplete combustion. Therefore, Kalman vortex shield can exist in Curzon flame. And this section, I will introduce my conclusion. Firstly, the methane flame case, we found the paradox flame extinction occur in the recirculation zone when vortex shielding occurring at the bluff body tail edge. In the Curzon flame case, we found that inadequate atomization and evaporation droplet, along with the insufficient mixing of the fuel and air, result in the low heat release rate within the recirculation zone, lead to the occurrence of Kalman vortex shield. Thank you for your listening.